All right, here we go. First office hours for Calc BC in the new work from home era. Do everything from home. This is worksheet assignment 3 from Unit 9. So this is all about series. This is a lot like what your next Unit 9 test will be like. So this is a really good worksheet. So I'm just going to do the questions that people ask for on the Google form. You guys have had 6 days to do this assignment since I gave it to you in class. What I want to encourage you is to use as many tests as you think you can use for each of these, just to get practice at all of them on your test. You're just going to use the one that makes the most sense if you can figure it out without having to do multiple tests. Now, if you do a test and it comes out inconclusive, then, whatever, try another one, leave the work. That's fine. But you need to name the test. You need to show all the specific work. So does the series converge or diverge? Justify your answer with a test, nth term, ratio, integral, comparison, alternating, geometric, and p-series. So those are all the different tests that we've talked about. And so we're just going to try them all on the ones that people asked for. So no one asked any questions about number 1, which could be a geometric series, so you could use that. I think nth term would be inconclusive, ratio, test, anyways, so forth. But number 3, let's zoom in here. Now, right off the bat, this is something that you're going to get better at. I'm looking at that and I'm like, oh, that's a P-series test. That'd probably be the quickest way to get it done. Least amount of work, conclusive answer. But let's just kind of go through and try the different tests. It's definitely not a geometric series, so we can't use that. It's not an alternating series, so we can't use that. So I'll just jump to the test I think would work the best. It's a P-series test, so we would write P-series test. I'm going to look for the name. And the p-value is 3. And the P-series test says if it's greater than 1, then it converges. Done. So that'd be the quickest way to do that. But let's try the other ones and see what they do if they tell us the answer with more work or whatever. So nth term test is probably a test I'd be doing in my head on once I get the hang of all this stuff. But for now, it might be good to just write it. Write the name. Limit as n goes to infinity of the nth term. And that goes to 0, which is good, but not good enough. It's inconclusive, which is usually the result for nth term test. We could try the ratio test, is the next most sort of common test. That's the limit as n goes to infinity of the absolute value of the n plus 1 term divided by the nth term, which if it involves a fraction, I like to cut to the chase and multiply by the reciprocal. And then try and simplify this. That goes to 1. And then these guys, you can't really simplify them. So if I were taking the limit, they're both the dominant terms. This is going to be n cubed. It's going to have some other terms, but this is n cubed, and you get n cubed here. As you go to infinity, the other terms aren't going to matter, and they're going to go to 1 also. So this goes to 1, which is inconclusive. So ratio test doesn't help us there. One of the other tests that we learned was the integral test, which is also, by the way, how we sort of developed our P-series test. So This one's probably going to tell us what the p-series test told us. So the integral test says if this function right here is positive and decreasing and continuous, which it is, if you think of it as just a regular function, then the integral test is appropriate. And what it says is to integrate the function as like a normal function, normal continuous function, and you get an improper integral. This is the same thing as 6x to the negative 3. So this is going to be power rule. So we would get 6x, you would add 1 and divide by the new exponent. And we're being lazy here and just writing all these infinities and stuff. I'd probably rewrite this as negative 3 over x squared first. And then if you were to plug infinity in, which technically you're not supposed to, you would get 3. Which means that this converges, this improper integral converges, and the integral test says, well, if that converges, then your original series is tied to that. And doesn't mean it converges to 3, but that means ours would also converge. So there you go. A few different ways to try that. Like I said, it doesn't make sense to use geometric test on this at all, or alternating series test. And comparison test is really last resort if nothing else works, because it's kind of hard to implement. I mean, we'll get a chance to see some of those, but so that's number 3. Number 5. Now, number 5, I see potential for trying to clean this up. So there's a 1/2 there. I'm going to rewrite this as n equals 4 to infinity of 8 over n to the 3 halves, right? Rules of exponent, you subtract from one to the other. And right when I see this, I'm like, oh, that's p-series. So the quickest way would be say, all right, let's use p-series test. If you have p-series test is going to be your quickest answer. The p-value is the exponent when it's in the denominator. So you don't write negative, it's positive, and you want it to be greater than 1. If it equals 1, that's harmonic series, which diverges. And if it's less than 1, it's going to diverge. But it's greater than 1, converges, done. That's your fastest route to an answer. Of course, we could try the other ones just to get good practice at them. Nth term test, which I would try in my head in the future once you get the hang of it and not bother to write it down if you know it's going to be inconclusive, which it usually is. Now, 10% of the time or whatever that it is conclusive, it's worth it. It's a test for divergence. So now I'm going to use my new simplified version of it, and that's going to go to 0, which is inconclusive. And all right, so that didn't give us a ratio test. Try that next. Generally, a ratio test for any p-series is going to be inconclusive, but we just get a little practice with it, I guess. Limits in goes to infinity, absolute values. This is all stuff you got to write if you're going to use these. You got to name the test. You got to show all the limit stuff. N plus 1 in parentheses to 3 halves divided by the nth term. And this is based off that idea that the terms have to be getting smaller. We derived this relationship from that idea. We could make those a 1. These are going to go to 1 when you take the limits in because infinity is going to be 1, which is inconclusive. All good stuff to write. And then on to the integral test, which, because it's p-series, I think this will tell us the answer, because that's how we came up with our p-series test, was by doing integral tests on a bunch of different p-series. So we're going to go, we got to make sure that, I guess we could go 4 to infinity, because my limits, I'm going to match them to this. And This is a continuous function. If we think of it as a continuous function, it's decreasing, it's positive everywhere. Those are just kind of general requirements to use the integral test. If those things aren't true, sometimes we can get around it. If it's negative, it's alternating, we could force it to be all positive and use the idea of absolute convergence. Anyways, when we write it in here, we treat it as an improper integral, and we think of it like x, like we were doing improper integrals in the last semester. Now, you might rewrite this as 8x to the negative 3 halves. This is a power rule. So we get 8x to the negative 1 half divided by the new exponent. Probably want to rewrite this. It's going to be negative 16 over the square root of x. And my infinities somehow became 8s. I guess they look kind of like 8s sideways. I'm going to realize, though, at the end, I hope I'm going to get improper integrals. So we get negative 16 over the square root of infinity minus negative 16 over the square root of 4 plus plus. That goes to 0. We're going to get 16 over 2 is 8. Which means it converges, which means our series must also converge. Not to 8, but to something else. So there's the long way of doing it a bunch of different ways. Number 7, someone asked about, now just to mix it up, this is definitely not a geometric series. This is not a P series. This is not an alternating series. So all those tests should not be used for sure. I don't see maybe a test right away that I know would work. So, I mean, in my head, I'm going to try nth term test, which I can already look at and say, yeah, if this goes to infinity, it's going to go to 0, which is good, but it's not going to tell me anything. So I probably wouldn't write this, but it doesn't take a lot of time to write. And it goes to 0, which is inconclusive. All right. Okay. I have a good feeling about this problem. I think more people probably should have asked about it, but we'll see. Okay. Try the ratio test. Ratio test. And write the name of it. Limit as n goes to infinity, absolute values of the n plus 2 factorial divided by the nth term. And we can simplify this using our knowledge of factorials. N plus 2 times n plus 1 factorial, right? Because any factorial is itself times the next smaller factorial. That allows you to get rid of those. So really, this is 1 over n plus 2, which goes to 0, which now you need to know if it's less than 1, that's convergence. So there we go. It converges based by the ratio test. So there we go. We got a conclusive answer. Now, I guess this could be maybe an interesting opportunity to try and talk about the comparison test. I mean, I wouldn't do it on this one because ratio test, which is pretty straightforward, worked very nicely. We could try a comparison test. Now, comparison test, the hardest part of a comparison test is you either want to find a series that your series is term for term smaller or equal to, that you know converges, so yours would have to fit under it and converge, or a series that yours is term for term larger or equal to, and the other series diverges, which means yours is going to diverge also. That's the hardest part, is picking a series to compare this to. Now, I mean, we already have a little bit of a sense that we know it converges, so I guess that gives us kind of a inside knowledge, but a series that is kind of similar to this, what you're going to do is you're going to look at the series, you might think, well, what's another series that's kind of like this? that I know converges or diverges or whatever. In this series, term for term is smaller than the terms in another series that's almost the same, 1 over n infinity. Now this is where knowing some of these other really common series is going to help you. Now this is actually one of our distinct series. Maybe right now you're not good at that. If we start writing the open form of it, you might remember from last chapter. It's 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial and on and on. And that might make you think of the e to the x Maclaurin series, 1 over 0 factorial. We could start at any term. 1 over 1. It's actually x to the 0 over 0 factorial, x to the first over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial. I don't know if you guys remember that one. So this is that, but the x value is 1. So this is the same thing as e to the 1. So not only does that converge, but it actually converges to the value of e. But it converges, I could say, and since ours are smaller, because if you start writing these terms, the first term is going to be 1 over 2 factorial, and then the next one's going to be 1 over 3 factorial, right? If you start writing the open form of this, they all have this extra 1 being added before you do factorial. So this is smaller than this. This is smaller than this. And term for term, every corresponding term is going to be smaller. So if that one converges, ours is going to be smaller than this. And the only way that it's going to work out is this one's going to converge also. So we'll say, therefore, it converges by the comparison test. Now, you got to make it very clear what series you're comparing it to and how you know that one converges, whether it's just one that we've memorized or one that you can show a test for. And you got to make sure we verify that all these terms are smaller than that. But anyways, that's a little example. Now, problem 9 down here is actually problems 1 through 8. Find the sum, which we rarely do right now, for all converging geometric series, because that's the only series we know how to find the sum of so far. And the sum was S equals A over 1 minus R. And so that applies to any problems that are geometric series, which were problems 1 and 2. So we'll go back and find that. And that's something I'm going to ask you guys to do on your next test. So you got to recognize that it's a geometric series. And if it is, then that's what you're going to do. All right. On to the back side. There were some questions in the back. So we'll try those. Let's see. Problem 11. People had questions. Now, big difference on the back is that these are power series, right? The ones on the front were number series. And how many x's? These all have x's involved. So usually we're not going to it's not going to be as simple as converge or diverge, which a number series is either converge or diverge. These are going to be converge, but where do they converge? They usually converge somewhere. In the rare case, some of them will converge everywhere. In another rare case, some of them will diverge everywhere, but that's going to be rare. Usually we're getting an interval of convergence, which we could also identify a radius for, which is just half the distance between the endpoints. But we also need, on the interval of convergence, we have to test the endpoints as their own individual number series. So usually what we do with power series is we don't do all those other tests. Most of those tests are for number series. We jump right to the ratio test. Unless it's a special case, then maybe one of those other tests might give you that it converges all the time or diverges all the time. Nth term test might tell you diverges all the time, but that's rare. So usually we're going to jump right to the ratio test. Take the limit. as n goes to infinity of the n plus 1th term. Be careful with, now don't add 1 to the x. We're adding 1 to the n value, or replacing the n's with n plus 1. And then we divide it by the nth term. And on free response, this is probably worth like a point. Like you set up your ratio test correctly. Got to write the limit, got to put the absolute values. Let's see if we can simplify it. We can get a 3 left over there, right? Rules of exponents. Here, we're going to get an x to the first power left over if we reduce those together. It's just all power rules. And then what's left is these guys, which if we take limits infinity, we're going to get infinity of infinity, which is indeterminate. We could do L'Hopital's rule and show all the technical, how it's going to actually work out. Or we could look at the dominant terms, and they're going to go to 1. So what we end up with is absolute values, 3 over x. So usually what's going to happen is after you take the limit, the n's should drop out. You should be left with an x. You still have an absolute value. And we want this to be less than 1 to converge for sure, conclusively. The endpoints, when it equals 1, we'll test those individually later. But we get an absolute value inequality, and we got to solve it. So using whatever, algebraic method, we could solve it. Now, it's a little weird with the x in the denominator. We could... solving this absolute value inequality, since it's less than 1, think of distance on the number line, that this has to be greater than -1, but less than +1 to get rid of the absolute value. So you could do that. And then you could, even in your head, you could be like, well, what values of x are going to make sure that this fraction is between -1 and 1? And so that would be x is between, and I think it's going to be like -3. Well, let's see. You want this denominator to be more than 3. So x is going to be either greater than 3, because then those would give you fractions that are less than 1. Or x is less than -3. And it's or because you're getting these two separate solutions. So this is kind of an interesting one just right now for the algebra. And instead of getting a single interval, kind of like in the middle or something, our answer is negative infinity to -3 and 3 to positive infinity. Now, the thing we still got to check are the endpoints. We're not checking infinity. Infinity just goes on forever. So it might be good to actually write somewhere in your work like, hey, these are the endpoints. I'm going to test them. And write that down. Write down which one you're doing. So we're going to say like x equals +3. And what we do is we plug that back into the original power series for x. And it gives you a number series. So if we rewrite that, and then we could, maybe clean it up. This is 3 to the n, 3 to the n plus 1. So rules of exponents would say, well, that's the same thing as n over 3 to the first power, right? And right now, I'm looking at that and I'm like, ooh, nth term test. That's again, the terms are just going to get bigger and bigger and bigger as n gets bigger. It's in the numerator. So we can say, all right, well, nth term test. So you're going to need to show the work for the endpoints, name the test, show the work for it, and it blows up. And it doesn't have to blow up to diverge. It it needs to not equal 0, which clearly it doesn't, so it diverges by the nth term test. And then we could try the other endpoint, x equals -3. Write down the work, plug it back in. I'll say this is one of the things that when you guys take your test next week, I'll probably be complaining about a lot of people. Now, this one, when you rewrite it, there's a couple things we could reduce the powers, simplify the powers, but then there's still a -1 to the n plus 1 power. Like I'm going to take that out. So and that could just be put in the numerator, -1 n plus 1. And then you have an n over 3. Now that's an alternating series. So you could try and use the alternating series test. But it doesn't go to 0. I mean, nth term test is going to blow up. So I'm going to do nth term test. Limit n goes to infinity. And this swings back and forth to infinity, which is definitely not 0, which means it diverges. And so we're going to end up going with the original answer. Neither of those diverge, so we're going to keep those as parentheses. Radius of convergence, I feel like doesn't make as much sense in this problem because it's not that typical, just single interval centered around the center. But so probably won't do radius of convergence for this one. But yeah, test the endpoints. All right, 13. So got another power series. So I'm going to start with the ratio test. So I these ones, I'm not doing a bunch of different tests. When you get to the endpoints, then all this variety of different tests that we learned that we're using on the front will come in handy on some of those. Absolute value, x plus 3 to the n plus 1. Now be careful on the bottom, it's going to be negative n plus 1. So that means you would have to distribute that if you want to get rid of those parentheses. Negative n over x plus 3 to the nth. That's going to be x plus 3 the first. This is negative n minus 1. Now, as this goes to infinity, it's really those largest terms that matter, and they're going to go to 1 because it's the same size terms. So we get absolute value, x plus 3. Absolute values are still there, and then we say, all right, it's got to be less than 1 to converge. And now we have an absolute value inequality. We're going to solve it. This one's a little more like what we're used to seeing. I like to use that ruler posit where I'm like, well, the center is at -3 and distance is less than 1 away. So let's go 1 away from the middle of that. We'll put open dots for now, and it's going to be everything that's in between those. So that'd be -4 and -2. But we got to test those endpoints. So that's where it might get some work. So maybe write a little note to me like, hey, this is what I'm doing endpoints, or a note to yourself in your work and tell me which one you're going to do. I don't know. I'll just do x equals -2 first. Write it down. X equals -2. Don't just say -2. Plug it in to so we're plugging in -2 in for x. It's going to be 1 to the n. Over negative n. And 1 to the n is just going to be 1, isn't it? So this is really -1 over n. I just moved that negative to the top. Now, this is not an alternating series because the negative doesn't have power on it. All the terms are going to be negative. You guys recognize that series, though? That's the harmonic series. So this is a harmonic series that's negative everywhere, which the harmonic series, when it's positive everywhere, diverges. If it's negative, it diverges in the negative direction. And I would accept that. I'd be like, hey, this is the harmonic series, and therefore it diverges. I'm all right with that. But just make it clear. Otherwise, have fun. You're probably going to have to do you could even say it's P series, P equals 1, fails, diverges. Otherwise, you're probably going to end up doing that integral test eventually. I think ratio test is going to be inconclusive and turn test is going to be inconclusive. I'm all right if you see something that's related to one of our really common series. Try the other one, x equals. Now, a lot of times what happens is one of them will probably be an alternating series. So that one was not. It just had a negative in front of everything. But where we got a positive 1 to the n power all the time, I bet we're going to get a negative 1 this time or something like that. Something different. So negative 4 plus 3 to the n power over negative n. And that's going to be negative 1 to the n power over negative n. And I mean, you might look at this and say, hey, and this is something you're allowed to do. You can bring that negative out front, any constant or anything, just like with, and do that. And you could be like, oh, that's the alternating harmonic series, which we know converges. Now, I'm all right with you writing that down, but you could, nth term test is going to be inconclusive, ratio test is going to be inconclusive, integral test is going to work, but you could also use the alternating series test. And the alternating series test says the limit as n goes to infinity of your series, if it goes to 0, it looks like the nth term test, but if it goes to 0, usually that's inconclusive for nth term, but for an alternating series, that means it converges. So I showed you guys that kind of back and forth motion of the partial sums with the alternating series. So however you want to do it. So it diverges for one endpoint and converges for the other. So negative 2 is going to stay open, but negative 4 is going to be closed. And your answer is negative 4 to negative 2, bracket on the negative 4, parenthesis on the negative 2. The radius of convergence is right in front of you. This doesn't rely on the endpoints converging or diverging. It's just going to be what is 1. By the way, I get right here, as soon as you get that x without a coefficient in front of it, that's your radius, right? I mean, you saw it right here. It's the distance from the center to the edges. So that's how we do that. Okay, let's try 15. Do another one of these. Okay, so we're going to jump into the ratio test for power series. Try and get that interval of convergence. So n plus 1 plus another 1 divided by the nth term. You guys should get good at just setting this up. Simplify it. You can simplify that. Rules of exponents. You get that to the first power. This is going to be n plus 2 times n plus 1 factorial. You guys should be getting good at simplifying that. And so what we get, I could just write it. Limit as n goes to infinity of absolute value of x plus 3 over n plus 2. And then we take the limit. I haven't taken the limit. I take the limit. It's x doesn't, we're not taking x to infinity, just n to infinity. So the bottom blows up. X is going to be some number. And it goes to 0, which is always less than 1, which means that this converges regardless of what the value of x is, which means it converges for all reals. And there's no endpoints to check because no matter what x is, you're getting less than 1. Done. So, I mean, that's kind of a weird case, but you should kind of like it because it's very... now, the radius of convergence, I guess you could say it's infinity. And radius is usually positive. Think like circle, radius of a circle. All right. And last problem, just one that's kind of totally different than the rest. But I talked to you guys about this. So this is a new way of estimating error for an alternating series. Now, it doesn't say anywhere in here explicitly alternating series. So you got to realize, I mean, you could use Lagrange error bound, but this might give you a better estimate, and this will for sure give you a better estimate. And this is way easier if you use the alternating series truncation error. So this right here, because it's an alternating series, and we're doing the fifth partial sum, and what we discussed is that the error between the current partial sum is for sure going to be less than the next term. And I kind of showed you guys this picture of, here's the first partial sum, and this is the answer it's going towards. And so then this distance right here is the next term to get to the next partial sum. And this is our error right here. And it's for sure less than this. And when you do the next one, this is your error exactly, and it's for sure less than this. And that's just always true. So fifth partial sum, our error is just going to be less than the sixth term. Now, we got to, it depends on where we're starting the series at. Fifth partial sum would be the sum of the first 5 terms. We could write them all out if you want, but n equals 1, 2, 3, 4, 5. 6 is the one we want. So we could just jump straight to the error is going to be less than the 6th term, which equals -1 to the 6th power over 6 cubed. And we're going to take the absolute value of it, and it's going to be 1 over 216. And so our error, that's not the error, but our error is less than that. It's an error bound. Now, if you're like, oh, that's confusing, how do I know for sure? And, what if this start n equals 3? How would I make sure? I mean, you could write the open form out. You'd be like, all right, well, n equals 1 would be -1 over 1, plus n equals 2 is going to be positive 1 over 2 cubed is 8, minus 1 over 3 cubed is 27, plus 1 over 4 cubed is 64, minus 1 over 5 cubed is 125, and there's first, second, third, fourth. This whole thing is the fifth partial sum. It's not the fifth term, it's the fifth partial sum. That's all the terms up to that point added up. The next one is what your error is going to be less than for sure. That's way easier in Lagrange error bound, so I'd recommend using it. But they're usually on the AP test. They're not going to just straight out tell you, hey, you should use the Lagrange error bound or alternating series truncation error. You're going to need to recognize it. And that's going to probably make a big difference. If it's not an alternating series and try and use this, then you're not going to get any points. If it is an alternating series and try the other one, I don't know. I mean, maybe you could get all the points, but it's going to be a lot harder work. And you might not have the information you need to even pull it off. So anyways, I hope this helped. And like I said, your next test is pretty much like this worksheet. So this is a really good one. You guys will have a pre-test. I'm going to do some notes right now that just kind of summarize all our different techniques. Might do a few examples and just talk about, which tests are the easiest So that's it.